Hello, my name is Jakub. During last 2 months, in cooperation with Enes Erciyes, I was working in Barcelona Supercomputing Center on project building resilient machine learning applications from HPC to edge. We explored neural networks as machine learning models because nowadays they are the most popular and are capable of achieving great results in many domains, such as computer vision or natural language processing. What are neural networks though? Neural networks are models which are loosely inspired by human brain. Each of them consists of multiple layers of units, so-called neurons, which are accepting data on inputs, returning result of computation on outputs, and learn from data with trainable parameters, so-called weights. Picture on the right side of the slide shows simplified schema of shallow neural network. We worked on the deep neural networks, what means that there were multiple hidden layers. We even worked with network with more than 150 layers. Deep neural networks are usually trained on HPC clusters because their training requires a lot of computing power. That's why training neural networks on edge devices is often not even considered. Only pre-trained models ready for inference are deployed. On the image, there is a schema representing components taking part in a distributed training process. On the left side, there is a data source, which can be standard hard drive, distributed file system, or cloud storage. Data is loaded by multiple processes concurrently. Loaded data is then collected into small groups called batches. Such batches are fed into training loop, which is run by HPC cluster, group of powerful computers, so-called nodes, with multiple GPUs on each of the nodes. There is also a checkpoint restart process ongoing concurrently to make sure training process doesn't have to start from scratch each time one of the compute nodes fails. Trained model is the final result of our training loop. Let's now explain shortly what is edge and what are edge devices as well. There are actually multiple definitions of edge and edge devices, but all of them are very similar to each other. Edge is a layer of not too powerful computing devices which are close to end user. By that, we can mean single board computers like Arduino, smartphones, or smartwatches. In our project, we tried to optimize deep neural networks so they could be deployed and used on smartphones. The main question is, why our project is relevant? Why would we want to deploy models on small edge devices when we have HPC clusters available? There are actually multiple reasons for that. First of all, sometimes we would want AI to process the data which is considered private. If model is deployed on a remote server, we need to send this private data through internet, what obviously is almost never 100% secure, and we are prone to private data leak. Secondly, sending data through internet causes significant latency, which can be avoided by storing model locally. Moreover, in case of internet connection unavailability, we can still use our model. Finally, deploying AI models on edge makes AI more ubiquitous and accessible, as most people have pretty powerful edge device at their disposal, like previously mentioned mobile phone or tablet. So now, as we know why deploying machine learning apps on edge is useful, we are moving to answering the question, how are we supposed to do that? In recent years, researchers came up with multiple ways to optimize the model, both spatially and temporally. Three of the most popular techniques are model pruning, model quantization, and knowledge distillation. We will go into more detail with pruning, as it's probably the most intuitive method. Pruning is a pretty simple way to make models smaller and faster. Pruning process removes least significant connections between neurons, as can be seen on the animation. Under the hood, it means setting the weights with smallest absolute value to 0. When most of the weights of the model are equal to 0, it can be more compressed. We can achieve up to 5 or even 10 times smaller model. Moreover, most calculations done on neural networks are addition and multiplication, which both are very fast to compute if one of the arguments is equal to 0, so we might gain significant inference speedup. On this slide, we wanted to share most important outcomes from experiments with pruning. We experimented with shallow model and small dataset to speed up experiments. We focused on comparing accuracy on test set, comparing training time, and compression we were able to achieve with pruning. Sparsity level equaling 0 means that model wasn't pruned at all. Sparsity 1 means that whole model was pruned. As it can be seen on the plots, it seems like around 80% of the model can be pruned without noticeable accuracy loss. This results in around 4 times model size reduction, from around 9 to just above 2 megabytes. Training time didn't change much with changing sparsity level, but there was a constant overhead in comparison with not pruned model. And last, but not least, graph showing the power of supercomputers and distributed training. Left side chart presents how using more GPUs during training reduced training time. It's important to notice that this is average epoch time, while training consists of 50 epochs at least, what means that with single GPU we have over 9000 seconds per epoch, which is over 2.5 hours, what means that with 50 epochs, full single GPU training would have taken over 125 hours, which is more than 5 whole days. With 32 GPUs though, we reduced single epoch time to less than 500 seconds, what means that whole 50 epochs long training took less than 7 hours. Right graph presents same data in other way. It compares how many times faster multiple GPU training is compared to single GPU training. And that's it for our presentation. Hopefully you found it interesting. Thank you for your attention.